Okay, let us consider the second problem. The statement goes like this. For the circuit shown below, find VC and VB. Okay, VC is collector to ground voltage and VB is base to ground voltage. Okay, so solution let's consider. So beta value is given. So beta is given as 120. Okay, solution. First let us mark the transistor terminals, base and emitter, and then let us mark the required voltages. Okay. VC from this terminal to the ground terminal, and we have VB from this terminal to, that is from base terminal to the ground terminal. All right, fine. So to solve this particular problem, okay, you have to apply Thevenin's theorem. So let's apply Thevenin's theorem. Okay, so as per Thevenin's theorem, any complicated network can be replaced with a simple network with one voltage source and a series resistance connected to that particular voltage source, so namely VTH and RTH. All right, so first let us find out RTH. To find RTH, what you have to do is you have to short circuit all the voltage sources. Okay, now before applying this particular step, that is short circuiting all the voltage sources, what I will do is I will draw the equivalent circuit first. Okay, the equivalent circuit, okay, by eliminating the load terminal. So the load terminal is anything that resides on right hand side of the base terminal. Okay, so this is my load terminal. Okay, load part. Now on the input side, what I have is base terminal. Okay, so that's my base terminal, and to the base terminal 8.2 kilo ohm resistor is connected, and to the same base terminal 2.2 kilo ohm resistor is also connected. So that is R1 and this is R2. Okay, fine. And yeah, and other end of 8.2 is connected to the power supply. Minus, this is 20 volts. Okay, and this one, the other end of 2.2 is connected to basically negative terminal of minus 20. Okay, so you can connect this to negative terminal of 20 volts. So the positive terminal is grounded. So this is what the circuit looks like. Okay, so that's your equivalent circuit for applying the Thevenin's theorem. All right, fine. Now the voltage measured across the open circuited terminal going to be your VTH. All right, on the other hand, RTH is found by short circuiting the voltage sources. Fine, so to find RTH, okay, what we will do is we will short circuit voltage sources. So what do we get by short circuiting the voltage sources? Okay, the supply is short circuited, and you will have 8.2 kilo ohm resistor and the 2.2 kilo ohm resistor. Okay, so this 20 volt cell is going to get short circuited as per Thevenin's theorem. So finally, you are left with two resistors connected in parallel. So basically, when you look into the network from the open circuit terminals, you will get RTH. So RTH in this case is R1 parallel with R2. That is R1 into R2 divided by R1 plus R2. So that's 8.2K plus 2. Sorry, multiplication 2.2K divided by 10 plus 2K. So that gives RTH value as 1.73 kilo ohm. Okay, so that's your RTH. Once RTH is known to you, you can find out the VTH. Okay, so to find VTH, what we will do is we will assume unknown loop current I. Okay, and VTH as defined earlier is the open circuit voltage. Okay, so let's assign the polarity for VTH. Okay, this is minus and this is plus. So VTH is equal to, okay, this is your ground node and this is your base node. VTH is equal to voltage across base to ground. Okay, base to ground. So that is VTH is equal to, okay, so through this R2 current I flows, right? So this current will produce a voltage drop across resistor R2 as shown. Okay, so we shall call it as VR2. Okay, so that's your first potential, and the second potential is the battery voltage measured from the negative terminal to the positive terminal. So when we write VTH, what we can do is we can write VTH as VR2. Okay, that's because minus to plus it is. On the other hand, 20 volt is appearing in phase opposition manner, right? So this becomes minus 20. All right, where VR2 is I into R2. All right, and I is equal to, okay, I is equal to, basically, you can apply, okay, to find I, you can apply KVL in the equivalent circuit. So what do we have? 20 minus 2 plus 20, then minus I into R1 plus R2. So that's 8.2K plus 2.2K. All right. Then minus to plus. So plus 20 is equal to 0. Okay. So current I is basically 20 plus 20, 40 divided by 8.2K plus 2.2K. All right. So that gives current value as 3.85 milliamperes. Okay, and you can find now VR2. Okay, so VTH is nothing but VR2. What is VR2? I into R2. So I is 3.85 milli into R2. R2 is 2.2K minus 20. Okay, so milli and kilo gets cancelled. So you will get VTH as negative 11.53 volts. Okay, so once you have VTH, you can reconstruct the original network. So in the original network, what do we have is you will have RTH, okay, and you will have the Thevenin's voltage source. Okay, remember one thing, the sign is negative. That means to say, you have to interchange the polarity. Okay, because the potential is more negative in nature. Okay, so I have reversed the polarity here, And let me claim VTH has 11.53 volts. Okay, reverse the polarity. Hence, I can write down the magnitude of the voltage source. All right, so that's my VTH. And this VTH, I am going to, this Thevenin's network, I'm going to connect to the load, right? What is my load? Load is nothing but the transistor circuit. So whatever you had removed while finding out VTH and RTH, you're supposed to insert back. Okay, so that's your emitter resistor. It is connected to RE. Okay, so other end of RE is connected to negative terminal of voltage source. And the voltage source value is 20 volts. And the positive terminal is grounded. Okay, so the positive terminal of VTH is connected to ground. All right, so that completes your, the input circuit. Now on the output circuit, you have your collector resistor RC and the supply voltage plus minus 20 volts. And this is then connected to the ground potential. All right, so this is my collector terminal. Hence, this voltage is VCE for me, plus minus. All right, and this voltage that is between base and emitter is VB. Okay, let's mark with the conventional notation, upper side positive and lower side negative. All right, and through RE current IE flows, that also you mark. Okay, on the output side you can also mark the required voltage. Right, if you remember, we had been asked to find collector to ground voltage. So collector to ground voltage is this. Collector to ground. Collector to ground. So this is the required voltage, what you are supposed to find out. Similarly, on the input side, you are supposed to measure the voltage between base terminal and the ground terminal. Okay. Okay, base and ground terminal. I will not mark VB here because the circuit looks bit messy if I introduce VB in my input loop. Okay, fine, fair enough. Now let me apply the KVL in the clockwise direction. Before applying KVL, let me mark the transistor currents. Okay, so through RTH, base current IB flows. What I'm doing, I am keep maintaining the NPN transistor current direction, right? Inward is the base current direction and outward is the emitter current direction. I'm just retaining the current directions as per, NPN transistor working. Fine, so let's apply KVL in clockwise direction. All right, so what do we get when we apply KVL in the clockwise direction? So I am sweeping this battery from positive terminal to negative terminal as minus VTH. All right, and then my resistive drop, IB into RTH, the terminal voltage minus VBE, because VBE is swept from positive terminal to negative terminal. Hence, it is considered as potential, fall. So minus VB, and then we have the voltage drop across resistor RE. So that's minus IE into RE. All right, and then the battery tracing minus to plus. So whenever I trace the battery from negative terminal to positive terminal, I get positive potential 20. Okay, and that is equal to 0. Yeah, that's equal to 0. All right, and if you look at the emitter current in the input loop, I do not want two currents. That is, I don't want IB as well as IE. So what I will do is I will replace IE with 1 plus beta times IB. Okay, so this substitution let us do. And what we will do is we will keep voltages on one side and resistive drops on the other, right? So what do we have? We have VTH as the first voltage, VBE as the second voltage, and 20 volts as the third voltage. So let me rewrite. Let me write it as 20 minus VTH minus VBE is equal to the resistive drops. All right. IB RTH. Okay. Then when I take it to the right hand side, the drops become positive. So IE can be written as 1 plus beta times IB into RB. Okay, so you can take out IB outside the bracket, and if you divide, okay, you will get IB is equal to 20 minus VTH. How much did you get? VTH as 11.53. So let me write it here, 11.53 minus VBE. For a silicon transistor, it is 0.7 volt. Not mentioned, but I'm considering it as silicon because silicon is the widely used semiconductor material, divided by, all right. So IB, I'm going to take it a common, right? So I will get RTH plus 1 plus beta times RE. All right. So let's calculate IB. So it is 20 minus 11.53 minus 0.7 divided by RTH. How much did we get? RTH as 1.73 kilo, right? So it is 1.73 kilo plus 1 plus beta, that is 1 plus 120 into RA. RA is 1.8 kilo. Yeah. So let's see how much we'll get the base current value as. So base current IB is equal to the numerator, you have 7.77. So this is 219.53 into 10 to the power 3. So base current is 7.77 divided by the denominator. So that will give you roughly 35.4 amperes, microamperes of base current. Okay, so once base current is known, you can always find the collector current. So that is IC is equal to beta times IB. So that's 120 times the base current. So multiply by 120. So that will be 4.25, approximately 4.25 milliamperes. All right. So collector current is known to you. Okay. Once this collector current is known, you can probably find VC. Okay. So VC is basically, VC plus IE into RE. Okay. We'll take this as equation 1. Okay. Next, let us apply KVL in the output loop. Okay, let me just give some color coding so that you'll be able to apply you'll be able to remember what exactly I'm doing in the main circuit. Right, so I'm applying KVL in the output loop in anti-clockwise direction, basically. So what do I get? I get VCC minus ICRC minus VCE minus IE into RE, which is nothing but my emitter drop, IE into RE. Okay, then anti-clockwise I'm applying plus 20. Okay, plus 20 is equal to 0. Okay, why plus 20? Because there is an external potential source exists. Okay, all right. Or okay, right. This I have missed it. So basically VC is collector to ground, right? Collector to ground is equal to collector to emitter plus drop across emitter resistor RE plus this 20 volt cell, right? 20 volt cell. Okay. So yeah, so what I will do, I'll just erase this. I'll not claim this as my equation. Let it be. Okay. Or you can do something like this. VCE is equal to bring VCE onto the right hand side. So what do we have? VCC plus 20 minus IC into RC minus IE into RE. Okay, so approximately you can write IC is approximately equal to IE. Hence, you can write VCE is equal to, let's substitute. What is VCC? E is 20, right? VCC is 20 plus 20. Minus IC. Okay, IC is 4.25 milliamperes. So let me write this as 4.25 milli into RC plus RA. So your collector resistor is how much? Collector resistor is 2.7 and emitter resistor is 1.8. Okay, so 2.7 plus 1.8 kilo ohms. So milli and kilo you can cancel out. So you're left with 2.7 plus it's 20.875. So VCE is equal to 20.875 volts. Okay, all right. So once you know VCE, okay, you can find out VC, right? So what I will do, I'll just recreate the transistor output connection. So this is your emitter terminal. This is your RE. This is connected to negative terminal. And this is connected to ground, right? This is minus and this is plus. This is 20 volt. And this is your collector terminal. So collector to ground is my VC. So collector to ground voltage is nothing but the algebraic addition of the three voltages. So upper side positive, lower side negative, and this is how the emitter current flows, right? Hence the voltage VE appears in this manner. Okay, where the current enters, that side we will take it as positive and this as negative. All right, and the 20 volt appears in an inverted manner, right? That is upper side negative and lower side positive. So VC, okay, VC is equal to VCE plus VE minus 20. That is equal to, what is VCE? 20.875 plus VE. Okay, what is VE? Here let me write, where VE is equal to IE into RE, or what is IE? 1 plus beta times IB into RE. So that is 121 into IB. IB we have obtained as 35.4 micro, 35, sorry, 35.4 micro into RE. RE is 1.8 kilo ohms. Okay, so just find out ammeter voltage VE. So it is 121. So that's 7.71 volts. So ammeter voltage is 7.71. So let's substitute 7.71 minus 20. So that gives VC as 8.58. 8.58. Okay, so VC we have found. Now we need to find out VB. Okay, VB is base to ground voltage. So what I will do, I will go back to the main circuit. Let me erase this and let me write VB. So VB is base to ground. Base to ground. So base to ground voltage is nothing but base to emitter voltage. Okay. Then emitter to ground voltage. That is, sorry, emitter to this particular node voltage, positive and negative, and finally this voltage 20. Okay, this side is negative and this side is positive. Okay, so base to ground, that is base is at higher potential and ground is at lower potential. So VB can be written as VBE plus VE minus 20. That is equal to VBE is 0.7 plus VE is 7.71 minus 20. So VB you will get it as 0.7, 7.71 minus 20. So that's minus 11.59 volts. Okay, so that is your VB. So this negative sign clearly indicates that base is maintained at lower potential at negative potential. Okay, so that is due to the insertion of external voltage. Okay, so that's your solution for the problem. Thank you.